Today we are talking about singly reinforced beam. Okay, what is singly reinforced beam? Singly reinforced beams are beams in which where reinforcements, if this is the cross section of our beam, reinforcements are given only on one side where the tension is to be taken. This is main reinforcement. Okay, this is the main reinforcement which takes the tension. If this is the beam, this is main reinforcement. This, it can be 3, it can be 4, it can be any number. Shouldn't be less than 2. Okay, and around that you will be having a shear reinforcement, or we call it as stirrups or shear reinforcements. These will be like this. This is the section and this is cross section. This is longitudinal section. Okay, and there will be a small, slightly lesser diameter bars in here. It is called as stirrup holders or stirrup holding bars. As the name indicates, these are only for just holding the stirrups at singular position, so that it does not lose its verticality. Stirrups shouldn't lose its verticality. So stirrups are tied onto each of these holding bars. This does not have any structural purpose, just for holding stirrups. Okay, so this is singly reinforced because it is reinforced only in one side. Doubly reinforced is there are only two kinds. Obviously, as you can imagine, there will be main reinforcements on both sides. This is doubly reinforced. In this case, there will be steel in the compression portion also, so that extra tension and extra load will be taken. Okay, there are many cases where double reinforced beams are used, and this is called doubly reinforced beams. Okay, and this top main reinforcements are known as compression steel. Compression reinforcement steel or compression steel. This is, as in here, tension steel. Okay, this is also called as tension reinforcement. This is for taking tensional force of beam, and this, as it is in the top portion, on the compressive steel. Compression, it takes compression. Okay, so that is singly reinforced beam, and we are rightly getting into problem. We will decide or will design a particular singly reinforced beam, and we will just get into it by doing a problem. Okay, so beforehand I want to tell you that you should have the IS 456 in your hand. All the details, all the equations, all the details, all the values we assume, all the values or tables we get values from are inside IS 455. You need to refer that IS 455 while at the problem. Okay, so I am going to give you a problem and we will do it together, and while doing it I will be displaying the page numbers of IS 456 at the bottom. So refer that pages, and you need to know where the pages are and where the informations are at the time of examination. Okay, so you just need to know where the information is. You will be having IS 456 on your hand at the exam hall. Okay, so it's very easy. You just need to follow some order. That's it. Okay, so you should have IS standards and calculator and a notebook, and please write down this question. So you have the question, and first and foremost information, simply supported beam. This beam is a simply supported beam. According to support systems, on the basis of supports given to the beam, you can classify beams into a number of types. First one is simply supported beam. Simply supported beam means, if suppose this is the beam, there will be simply supports. It's like on two stones, another horizontal stone is kept, beam is kept, no fixation, just it is resting on two supports at the two ends. That is simply supported beam. And there is cantilever beam. You all know this. There won't be one support, but the other support will be strong enough. This is cantilever beam. Okay. And continuous beam. Continuous beam is similar to simply supported beam, but it will be continuous as it goes on. This will be a somewhat longer beam. There will be supports like this. Okay. The supports will be continuous and beam will be continuing throughout the supports. So these are the most commonly referred types of beams, and right now we are concentrating on, the question is asked on simply supported beam. Okay. And you know the span is 4.5 centimeter span. Okay. The span means 4.5 meter. Okay. This distance is 4.5 meter. Right. And there is UDL. UDL means uniformly distributed load. That means there are a number of loads. First one is point load. Point load is just a single load. Okay. And next one is UDL. UDL is uniformly distributed. As the name indicates, the load is uniformly distributed. We express it like this. Okay. Like this. And this, its value is 33.375 kilonewton per meter. On each meter length of this beam, we have 33.357 kilonewton of load. Okay. And there is one more, uniformly varying load. That is, there will be distribution, but at one end the load will be 0 and the other end load will be maximum. Okay. So these are the basics you should know. Okay. So uniformly distributed load value is 33.375, and you know these two values. M30 is the mix of concrete. That means the strength of concrete will be 30 Newton per mm square of a casted concrete cube. Okay. And Fe 500 means the steel will be having, this is of concrete and this is of steel. You learned it earlier. This is 500 Newton per mm square strength in tension for steel. Okay. These are the main informations given, and we have a starting point. What is the starting point? Starting point is, first one will number each of these values that we are calculating, and you should have an order. Okay. First one, width of beam, and as in question, it is said that it can be assumed as 300 mm. Okay. Width means if this is the cross section, this can be 300 mm. cross section like this. Okay, so this is given. You can assume 400, you can assume 250, it's your wish, or it is not wrong if you take 350 in this question. You can take 250. All the values will change obviously. Your depth will be changing, your many values of what we are doing in next coming minutes will be changing, but it does not matter. Okay, if you have the right procedure, you are on the right way. There is no mistake. In design of any concrete structures, if you are following a particular procedure and if there is no mistakes in that procedure, you are right. There can be variations between two correct answers. Okay, so keep that in mind. You don't want to stick on to single values. Okay, so width of beam can be assumed as in question 300 mm, and second one, depth of beam. Depth of beam can be calculated by the equation L by D is equal to 10, where L is span and D is depth of beam. Okay, so span is 4.5 meters. 4.5 meters divided by 10 will give you D, that is 450 mm. 0.45 meter, that is 450 mm. Okay. Third one, you need to find out effective depth. What is effective depth? So you have a beam like this, and you will be having a number of main reinforcements, and you will be having a stirrup like this. Okay, there will be stirrup holders. Effective depth D dash is given by the top fiber having compression to center portion of main reinforcement. Okay, is it clear? Effective depth is the distance between the top portion of a beam or the compression taking farthest compression taking fiber of a beam, that is the top portion, to the midpoint of main tension taking reinforcement. Okay, so this point at the midpoint is taken as D dash. Okay, and the remaining is called as effective cover, because we are taking the effective depth when we are considering effective cover. There is a clear cover in here from the stirrup, nearest end of stirrup to the farthest end of tension taking concrete is called as clear cover, and the remaining portion from D dash is known as effective cover, and clear cover is expressed as C and effective cover is expressed as C dash. Okay, so as you know, there are two covers, clear cover and effective cover. We know the depth of beam 450 mm. If we know the stirrup reinforcement diameter, this line, single line, this will be a lesser diameter bar, right, stirrup. And if we know the main reinforcement diameter, we can calculate effective depth, right? Okay, so according to code IS 456, clear cover is taken as C, can be taken as 20 to 30 mm. Okay, so we are taking it as 30 mm. You can take 20 or 25 mm. Okay, so we have clear cover as 30 mm, and we are assuming this stirrup, this lesser diameter bar or shear reinforcement bar, as diameter of shear reinforcement as 8 mm. 8 mm bars are used as stirrup. Okay, and diameter of main reinforcement bar are taken or assumed as 20 mm. These bars, these three bars are 20 mm, and the stirrup is of diameter 8 mm. We are talking about diameter. Okay, so we have the clear cover and we have the diameters of these two bars. We want to have effective cover from these values. Okay, so effective cover will be C dash will be equal to clear cover 30 plus 8 diameter of stirrup plus half of main diameter. At the midpoint we are talking about effective cover, right? So 20 by 2, that is 48 mm. That is effective cover. Then what is effective depth? D dash is equal to depth of beam minus effective cover. Depth of beam is 450 minus effective cover is 48. That is 402 mm is effective depth of D dash. Okay, and one more, we will go one more step. Fourth step, it's pretty simple. What is FCK? FCK for the design of concrete, characteristic strength of concrete is termed as FCK. We have talked about this, and FCK is directly this value 30, right? And what is Fy? It is just this particular value, that is 500. Okay, so moving on to next one. So we have effective depth as 402 mm for the record, and total width of beam is 300 and depth is 450 mm. Okay, and next one, fifth one. Effective span of beam. As we know, clear span is given as 4.5 meters, right? So what is effective span? Effective span can be calculated by two ways. You have to take the minimum of these two calculations. The first one is clear span plus effective depth, that is 4.5 plus 0.402. 0.402 is effective depth, that is 4.902 meters. Okay, the second method is if you are taking this beam like this, and the beam will be supported on, we are assuming that you will be supported on a wall, okay, and we are assuming the width of this wall as 20 mm, okay, 20 mm here and 20 mm on that, okay. And second method is center to center distance between supports. The clear support distance is 4.5. So what will be the center to center distance? Center to center distance will be 4.5 plus 20 by 2 plus, or 0.2 by 2 plus 0.2 by 2, that is 4.7 meters, okay. And you have to select the minimum of these two, so you will select 4.7 as effective span, okay. Sixth one is kind of an important one. We are coming to loads. Load calculation. Okay. And you know UDL is given as 33.375 kilonewton per meter. In addition to this external load of 33.375, you will be having self weight. This much amount of concrete of 4.7 clear span, effective span effective 4.7 meter effective span is supported on the walls, right? So you need to have consider the weight of this particular beam. This is a massive weight, so we will calculate the self weight. The density, mass weight density of concrete is given as 25 kilonewtons per meter cube. So 25 multiplied with total width and total depth. We will not consider effective depth because we are considering the whole weight of this concrete. So total width and total depth. 25 into 0.3 into 0.45. You will get 3.375 kilonewton per meter. For each running meters, you will be getting this much weight, 3.375 kilonewton. Okay. So what is the total UDL? As you know, you are having an external UDL of 33. In addition to that, you are having self weight of 3.375 per meter. So we will just add up. Then we will consider it as a single UDL. Okay. So total load 33.375 plus 3.375, that is 36.75 kilonewton per meter. Okay. And then we will consider bending moment. This is important. You need to remember this. Bending moment equation for simply supported beam is WL square by 8. You need to know that. Okay. WL square by 8. For cantilever beam, if it was, instead of simply supported beam, if it was cantilever beam, it would have been moment is equal to WL square by 2. Please note that. Okay. So for the time being, WL square by 8, where W is 36.75 L is effective span, and 8 L square by 8 you will get bending moment of this particular beam. Okay, so 36.75 into 4.7 square by 8 you will get 101.48 kilonewton meter. Okay, next point is important. Next point is 7th one. As you know, in limit state method, we are doing it by limit state method. As you know, limit state method, you will divide the strength of each materials F30 or Fe500 by a particular factor, 1.5 something else, 1.25, 1.15, etc. Right? And what you will do with loads, you will multiply with a factor, right? If you remember it right. So you have this bending moment, and for safety purposes we are multiplying, amplifying this load so that we will be able to design this beam as a better beam, so that it will compensate for additional load if it comes. Okay, so instead of 101.48 we will consider fractured load as 1.5 into 101.48, that is 152.22 kilonewton meter. This load will be taking into consideration. Okay, so we will multiply it, we will add 50% more, so that even if this load changes by any value, the beam will not fail. Okay, that's the theory of LSM, limit state method. Okay, fracture load is 152.22 kilonewton per meter. Then 8th one, check for mu limit. So in IS code, you have a particular table for each Fe value. Okay, as it is 500, its value is mu limit value is given as 0.134 FCK BD square. Okay, you just need to substitute FCK as 30, B as 300, D as effective depth. Effective depth is 402. Okay, so you will get 194.89 kilonewton meter. Okay, this is the mu limit of Fe500 or this particular beam, considering FCK, B and D. Okay, so this is the limit. So you please pay attention. This value you got it from the code itself. Now we will compare between these two values, our fractured load and mu limit load. Okay, if our fractured load is less than mu limit, then we will design it as singly reinforced beam, like this. If it is greater, if in this case we are safe, we can design singly reinforced beam, because 152 is lesser than 194. Singly reinforced beam. If suppose it was about 200, then fracture load will be greater than mu limit, then you have to design doubly reinforced beam. You know what they are, right? So for the time being, as factored load is less than MU limit, singly reinforced beam can be designed. Okay, that is important. Moving on. Ninth one, AST calculation. AST means simply the area of steel. That means the area of main reinforcement. Area of main reinforcement. That is AST. Okay. So as per the IS code, we will have an equation called moment of resistance, MR, is equal to 0.87 Fy AST into D 1 minus Fy AST divided by FCK BD. As per IS code, you have all the values in here known except AST at two places. Okay. So what is MR? MR is MU, or the fractured load we are just find out. MU is equal to 152.22 kilonewton meter. We just found out. And what we compared with MU limit, right? That can be also called as MR. MU or MR, moment of resistance, or MU. Okay. So MR, we know what is MR is. 0.87 into Fy is 500. AST we don't know. D is effective depth 402 mm. Fy again 500. AST we don't know. FCK is 30. B is 300. D is again 402. Okay. 152.22 into 10 raised to 6, because we want our AST in mm square. MU is given as kilonewton per kilonewton meter. So you want to convert it into Newton millimeters. So for making it in Newton, we need 10 raised to 3, and for getting meter into millimeters, you need again one more 10 raised to 3. So this value into 10 raised to 6, you will get Newton mm. Okay. So just so you understand. So that is 0.87. Fy is 500 into AST into 402 into 1 minus 500 into AST divided by 30 into 300 into 402. So this will form into a 2-degree quadratic equation of AST. So in calculator, using calculator, you can solve it as AST is equal to 6223.8 mm square and 1012.016 mm square. So obviously we will select the minimum value, because we don't want to put maximum AST into it. Maximum, we just want minimum value. It's okay if you put 623.8, but it will be having major cost issues. As you know, steel is much costly item, so we will select 1012.6016 mm square. Okay. So AST is equal to 1012.016 mm square. Okay. Next one, check for AST minimum. We want to check the AST minimum value, minimum criteria with our obtained AST value. As you know, AST is right now taken as 1012.016 mm square. Okay, so in this section you need to have main reinforcement of this much area. That is the idea, AST. Okay, so check for AST minimum. The equation is AST minimum is equal to 0.85 BD by Fy. You know this value is 0.85 into 300 into 402 divided by 500. You will get it as 205.06 mm square. As this value AST minimum is lesser than our chosen AST value, it is on the safe side. Okay, hence checked. Okay, then one more, check for AST maximum. AST maximum of any beam is given as 4% of total cross section area. That is 4 by 100 into total area means 300 into 450, total area, right? Not effective area, total area. So AST max is equal to 5400 mm square. So these are the limit. Our chosen AST shouldn't fall below 205 and shouldn't exceed 5400. Okay, so hence checked AST 1012 is safe. Okay, there we have checked it. Then the next one, how will you provide this? The number of bars. You can provide 20 mm if 20 mm dia bars are provided. We had assumed 20 mm in our clear cover scenario, right? If you want, we can change. Okay, it was just an assumption. Based on that assumption, we calculate all these things. But there is the possibility of slight change of diameter. You can change if you want. You want to know how much number of 20 mm diameter bars are to be used. Okay, so if 20 mm bars diameter bars are used, how many will have to be used? Number of bars is equal to 1012.016 divided by area of a single 20 meter bar. What will be that? Pi by 4 into b square. Right, b square is 20 square. Okay, so this is the area of a single bar dividing with the total area. With a single bar area, you will get the number of bars, that is 3.22 numbers. So we cannot round it into 3. It will be lesser than 1012. So we will be taking it as 4 bars. Okay, if you think 4 bars is unreasonable, if you are wasting some portion of this area, we can always consider 16 mm dia. Then number of bars is equal to 1012.016 divided by pi by 4 into 16 square. You will get around 6 bars. But according to calculations, using 6 bars of 16 mm dia is economical than 4 20 mm dia bars. Okay, so that's why we are selecting 6 bars of 16 mm dia. Okay, next one. So we have almost completed the problem, the design. We have till the AST, main reinforcement. Okay, so with this much information we can start drawing the cross sections, this figure neatly as possible with the namings, and also one more figure like this with this as the supports, and 4.5 meter clear span like this, 20 mm support length, and with tension bars, stirrup holders and stirrups. Okay, and as for stirrups, you need to have one more step. Okay, so as I said, more major portion is done, you need to have 2 more steps. Okay, and that is check for shear. Check for shear is calculated by first calculating shear force. Shear force is the force which is acting by which this, if suppose we take a section and I am applying a upward load in here and a downward load in here, there will be a force for tearing about, right? That is shear, and we need to compensate, or we need to contain that force in that beam also. Okay, that is why we are providing these stirrups. Okay, so first we will calculate V, that is shear load. So shear load is equal to WL effective by 2, that is 36.75 into 4.7 divided by 2, that is equal to 86.363 kilonewton meter. Okay, so we have shear load, and as always we will also multiply it with this load also. As this is a load, we will multiply this with 1.5 into 86.363 to get VU, or fractured load. Okay, so that is 129.54 kilonewton meter. Okay, so we have the fractured load for VU, as in bending moment we have expressed as MU. So in here we are expressing it as VU because V is shear load. Okay, and for this, to calculate how much stirrup should be given, we now need to calculate shear stress. Shear stress, that is tau U, is calculated by just dividing 129.54 by BD. For general equation is VU by BD. Very basic equation. For calculation of stress, you will divide the load with area. Right. The area is this cross section area. We are considering a single section. So this cross sectional area is given by B into T. In this is used as effective diameter or effective depth. Okay, so tau u will be given as 1.07 Newton per mm square. So as you must know, you need to convert VU into millimeter terms. Okay, so you will get shear stress as tau u 1.07 Newton per mm square. Now you need to calculate two things and you will get those values directly from IS code, and those values are tau C and tau C max. Okay, by comparing this value, that is tau u, with these two values, we will then go forward. Okay, so these two values will be directly taken from IS code. For that we need to have some more values, that is PT. PT is percentage of reinforcement, main reinforcement, that is Ast by BD into 100. That is pi by 4 into 20 square into 4. There were 4 bars, right? Into 100 divided by 300 into 402. That is 1.04%. So in this cross section, 1.04% of area will be covered with AST. Okay. So using PT and tau V or tau U, you will get PT and tau V, you will get tau C and tau C max from IS code. Okay, please refer those tables and take these values by yourself. In this, tau C is given as 0.66 Newton per mm square, and tau C max is given as 3.5 Newton per mm square. Okay, so for the concept, tau C max is the maximum value that can be taken by a stirrup. Okay, so it shouldn't normally, this value, which value 1.07 tau u, tau v or tau u shouldn't increase above this particular value. Okay, and this tau c is the value with which this main reinforcement takes shear. Okay, as you know, there is 1.04 mm square percentage of area of this whole cross section covered with main reinforcement, right? Main reinforcement. So this can also take some portion of shear, and that portion of shear is 0.66. Okay, if you don't understand this, leave, it's not so important. I just telling you for the concept. That is 0.66, the portion of shear that takes up by the main reinforcement only. Okay, so that portion 0.6 will be taken by main reinforcement. These stirrups should take the additional value. Additional value means 1.07 minus 0.66, right? Okay, so with these two values taken, we should compare these three values as I said earlier. So right now it is like this: tau C is less than, tau V is less than tau C max. Okay, and suppose tau V, this one we found out using V from the beginning onwards, tau V was less than tau C, that is 0.66, there is no question. We need not design shear reinforcement or stirrups. We can just provide these stirrups for namesake. These stirrups need not take any shear. All the shear will be taken by main reinforcement. Okay. As tau V is greater than tau C, that is 0.66, 1.07 is greater than 0.66, you need to provide shear reinforcement. Okay. So shear, this reinforcement is required. Okay. So as you have tau V 1.07 greater than 0.66, you need to design this particular shear reinforcement, and the equation will be with respect to load. VU S, that is the shear load should be taken by the shear reinforcement. VUS will be equal to VU minus VC. VC is, this is stress 0.66. We need to convert it into load. How do we do that? VU minus tau C into BD. So the general equation was V is equal to, as earlier we had tau stress is equal to load by BD, right? Same equation. VC can be substituted with V tau C into BD. Okay. So substituting VU is 129.54 minus 0.66 into 300 into 402. Okay, so you will get 49944 Newton or 49.499 Newton, right? Kilonewton. 49.944 kilonewton. Okay, so using this value, only for 49.9 value you need to design shear reinforcement. For that, VUS is equal to 0.87 ASV FYD divided by SV. Okay. Where ASV is area of stirrup or shear reinforcement. We can assume that. Okay. And SV is spacing of stirrups. So this spacing, this is the SV. If in longitudinal section, this much spacing, these stirrups will be placed. Okay. So SV is the spacing and ASV is the area of stirrup. Okay. So from this you have VUS as 49.944 kilonewton. You have 0.87, FY as 500, D as 402. SV we will calculate. We will substitute ASV as, if you are taking two legs like this. Okay. So for this section we are only considering two legs. That means 2 into 1, 2 into 8 mm dia. Remember, at the initial stage, 2 into pi by 4 into 8 square. This is ASV. For any particular section, we are assuming 2 legs of stirrups like this. If it was 3 legs, you would have to provide like this. So we are not providing it because it's a complicated design. We need to work more. Okay. So mostly we will decide on 2-legged stirrup. Okay, 2 into pi by 4 into 8 square. 8 square we had decided earlier. Okay. So substitute that in ASV, you will get SV in mm. So for getting SV in mm, you need to have all these things in mm also. So SV, you will get it as 351.99 mm approximately. We can round it as 350 mm because it is spacing. You can round it backwards. It shouldn't be greater. Okay, so 350 mm. Okay, and checking for maximum spacing of shear reinforcement. We have two criteria, either the minimum of 0.75D or 300 mm. Minimum of these two should be the maximum spacing of shear reinforcement. Okay, so we have obtained 350 mm. So evidently it wouldn't be 350 mm as you can see. So 0.75 into 402, you will get 301.5 mm. Okay, so 301.5 mm and 300 mm. The minimum of this 300 mm. So as the spacing should not exceed 300 mm, you will not consider this. So the spacing will be 300 mm, and hence the inference is shear reinforcement will be two-legged 8 mm dia bars with 300 mm spacing. Two-legged 8 mm dia bars with 300 mm spacing. That is the inference. Okay, so that was shear reinforcement design. We have one more step. So we are getting to the end portion. Last step, check for deflection. Okay, check for deflection. We are just checking an L by D ratio. Okay, so there is an equation called L by D maximum L effective by D maximum is equal to L effective by D basic into KT into Kc. Okay, so I'll just say the concept. We will calculate L by D maximum using this equation, and we will check whether our L by D ratio of this beam using L effective, we have L effective as 0.7 and D as 450. We will decide it, compare with this value. If our L by D is less than this maximum value, we have checked for deflection. Okay, that's it. So for calculation of L by D maximum, this value can be taken from the IS code itself. For simply supported beam, it is given as 20 directly. For cantilever it can be 7, for continuous it can be 26. Okay, so KT is correction factor for tension reinforcement, KT, and Kc is for compression reinforcement. Correction factor for tension reinforcement KT and compression reinforcement for Kc. Okay, and the good news is you don't have to calculate Kc. Kc is 1 because there is no compression reinforcement. In double reinforced beams you need to calculate Kc also. Okay, so as there is no compression reinforcement in our beam, singly reinforced beams, any single reinforced beam, you can substitute directly 1. You need to calculate KT. For that there is a table in IS code, and from that graph you need to get the value of KT you need to plot the values of PT and Fs. We know the value of PT as 1.04%. We just calculated earlier for shear. And Fs is equal to, there is an equation, 0.58 Fy Ast required divided by Ast provided. Okay. The only thing you need to know is Ast required was 1012, right? So 0.58 Fy Ast required 1012.016. Ast provided was 4 bars of 20 mm dia, right? It was greater than 1012. That value 4 into pi by 4 into 20 square was Ast provided. We are talking about main reinforcement only. Okay, and the value was 233.56 Newton per m square. Okay, so using PT as 1.04 and Fs as 233.56, you can calculate or you can get KT from the graph given in IS code as 0.85, and we know Kc as 1. So L effective by parameter is small letter d. D maximum value is equal to L effective by D basic, that was 20. 20 into KT was 0.85 into Kc was 1, that is 70. So this is the L by D maximum value. So L by D of our provided L by D ratio should not exceed this value. So L by D, L effective by D provided is equal to, L effective was 4.7, D was 402, that is 11.2 or something. Okay, so comparing these two, it did not exceed our L by D ratio, provided L by D ratio did not exceed the maximum limit 70. Okay, so as it is less than maximum value, the beam is safe in deflection. So we were checking for deflection. As 11.2 is less than 70, the beam is safe in deflection. Okay, so that's it for the design of singly reinforced beams. So this much steps should be done, and the last two steps may seem a little elaborate, but they are too simple. You just need to have IS code and its page numbers. Okay, so with the order of particular designing, you just can do like a flow. Okay, you just need to get a flow. You just rewatch this, do this problem again in your notebook by yourself using the question given, do some more problems and do the question given at the end, work out more problems, and it will be too easy. Don't consider this as it took this much time. Do not consider this problem as a difficult one. Very simple problem, and you have the materials with you. It's very easy to do. Okay, so thank you.